Welcome to this DEEPLIZARD course on diffusion models. I'm Mandy, and in this lesson, we'll be exploring all of the components within Stable Diffusion. Latent diffusion models like Stable Diffusion actually make use of many different models and tools for training and inference. So let's look at the components of Stable Diffusion. We have something called UNet, we have a noise scheduler, we have a text encoder called CLIP, and a VAE, or a variational autoencoder. We're going to get a general overview of each of these components in this lesson, and then later in the course, we will expand much further on each and every one of these. So let's start with UNet. At the core of Stable Diffusion is a neural network called UNet. UNet is a type of convolutional neural network where training and inference take place to generate the images that we are used to seeing with these latent diffusion models. As depicted here, we can see that UNet receives images as input, and it also gives images as output. And actually, these images are compressed images that we refer to as latents, but just for our introductory purposes here, we are going to imagine that we are receiving and outputting images, but just know that they are compressed images or latents. The first half of UNet, as shown on the left here, is made up of convolutional layers. And as we know, convolutional layers will downsample the input data. And so this left-hand side of the neural network is referred to as the contracting path. This second half of the network is made up of upsampling layers. And as depicted here, the upsampling layers are upsampling the data that gets passed to them. So contrary to the first half of the network that is downsampling and referred to as the contracting path, the second half of the network is upsampling the data and is referred to as the expanding path. And when we combine the contracting path with the expanding path, we see that we get this depicted U shape, which is where the name UNet comes from. We'll expand much further on UNet and the details of this model, the architecture, what exactly is happening during this downsampling and upsampling during training and inference to generate images later in the course. But for now, we can just understand that UNet is the meat of the Stable Diffusion model, and it's what is responsible for generating images. Now let's talk about our text encoder. As we've become familiar with, whenever we are working with the latent diffusion model, we pass a text prompt to it to specify what types of images we want it to generate. And like most data that is passed to neural networks, we first have to process this text data. Specifically, the text data has to be processed or be encoded from the original text into a text embedding. And to do this encoding, we use a model called CLIP. And here we can see what these embeddings might look like. And if you're not familiar, a text embedding is just a numeric representation stored in vectors that has encoded some semantic meaning behind the underlying words in the original text. So these text embeddings are what get passed to our model as the text portion of our input. And if you'd like to learn more about embeddings and understanding them more fully, then check out our natural language processing intro course on DEEPLIZARD.com. Now, we said that we are using CLIP to do this encoding. So this is a step before training and inference take place with UNet. We are processing our text input with CLIP, which is a pre-trained model. And let's just scroll down a little bit where we have depicted what CLIP is doing. So unlike a typical text encoder, CLIP is actually trained not only to encode text, but also to encode image data as well. Specifically, it's trained on text-image pairs like we've depicted here. We have the text, kettlebell, dumbbell, and barbell, along with their corresponding images of a kettlebell, dumbbell, and barbell. And within CLIP, each of the images are encoded into these image encodings, and each of the texts are encoded into text encodings. And each of these encodings are a numeric vector, otherwise known as an embedding. Now, this is just a little preview into the CLIP model. Again, we're going to be expanding much more on how this model works and what exactly we're doing here by taking the dot product between the text image pairs in a later lesson. For now, we can just understand that this clip model is being used to encode our text prompts into embeddings before being passed to our model during inference and training. Now let's move on to the VAE, otherwise called the variational autoencoder. As we mentioned earlier, latent diffusion models work with compressed latent representations of images. As input, along with the encoded text, like we just talked about, those text embeddings, UNet is also going to accept image input, as we alluded to earlier. Now, these latent representations of our original image data, so these compressed images, are actually going to have noise injected into them. So it's these compressed noisy images, or these noisy latents, that are going to be the image input that is sent to UNet. This compression from original image data into latent representation is going to occur using the encoder portion of a variational autoencoder. And so as depicted here, we have an image here that has some noise injected into it. And once we pass that image to our encoder from our autoencoder, it will give us an encoded representation that we are going to refer to as a latent. And we can think of this latent as just being a compressed version of our original noisy image. And this is what happens during training. During inference, we make use of the decoder portion of our VAE. Recall, as output, UNet is going to be giving us a latent as output, and so we use the decoder to decode the latent back into an image. Now, this is just a depiction of a general autoencoder, which is being used to reconstruct a noisy image. So we are passing in this noisy image, it's getting encoded and then decoded so that the image is reconstructed and to be a more clear and less noisy image. But the takeaway for latent diffusion models is that the encoder is being used to compress our original image into a smaller version referred to as a latent, and the decoder is being used to reconstruct that latent back into an image during inference. So UNet is working with these latent representations of images so they are smaller, using less data. And then after we get our latent from UNet, we can blow it back up into an image. So we've seen UNet is what is actually being trained and used for inference purposes to generate our images. We have our clip model being used as our encoder to encode our text data into embeddings. And then we have a variational autoencoder, which we are using to encode and decode latents into images and images into latents. Now, the last major component that we will discuss in this lesson is the noise scheduler. So we discussed how the input to UNet, at least the image portion of the UNet, are going to be these compressed noisy images or these noisy latents. The way in which noise is added or injected into these latents is done by what is referred to as a noise scheduler. The noise scheduler samples noise from some set distribution and then adds the noise to the images according to a set schedule. So in this illustration, we are showing how noise might be added over time. We have these time steps ranging from 0 to 4 in this example, and we can see that the noise is increasing over time here. And this noise is added to images during the training process, or before training begins rather. And we'll see actually that during inference that we do denoising, where we are removing the noise that has been added. This concept of adding and removing noise from images over time may seem a bit abstract now, but we are going to completely solidify these concepts in later lessons. So now we should at least have a general understanding of the 4 major components involved in Stable Diffusion.